webinar too? Okay, so welcome to everybody who's here in person and also to those that have logged in on the webinar. I think we have 4 or 5 sites logged in on our first inaugural webinar for this group. So hopefully all the technology works smoothly and we can, everybody will be able to see and hear the presentation. I'm very, very pleased to welcome Cheryl Glazebrook, who's agreed to come and speak to us today. She is an associate professor in kinesiology and recreation management at the University of Manitoba and the director of the Perceptual Motor Integration Lab. How applicable does that sound to what we do? So I heard Cheryl speak at a presentation at McNally Robinson, and I think, Jean, were you there as well? And Jean and I put our heads together and we're like, let's get Cheryl to come talk to our group. And it took a little bit of doing because I think that was maybe last March or something like that, but she's agreed to come speak to us today and we're really, really pleased to have her. So please welcome Cheryl Glazebrook.
There we go. Whoops, see, already. I like how I know the thing that makes me most nervous is microphones. Okay. I'd like to thank Marie for the invitation. It's really exciting to speak with your group. I think I spoke to at least some of you when I first arrived in Winnipeg. It's very clear I've been in Winnipeg now since 2010 because I think there's somebody from almost every walk of my life here today. So I think that makes me officially a Winnipegger. So thank you very much. I'd just like to start by acknowledging that we are on Treaty 1 territory and that this land is the traditional territory of the Anishinaabe, Cree, Ojibwe, Dakota, and Dene people, and the homeland of the Métis peoples. Okay, so augmented and alternative feedback for motor skill learning. This presentation and the research in it wouldn't be possible without my wonderful group of students. You'll see that many of the graphs and work has been driven by them. So I'm here to pull the pieces of the puzzle together and share the story, but this work would definitely not be possible without that group. And I'd also like to thank the various funding agencies that have given us the funds to be able to support this research, as well as the many participants who, without this research, we would definitely not have been possible. All right, is it possible to get this slightly higher? Slightly. There, is that good? Is that okay? Okay. All right. So my goal for today is to share some of the research from my lab, as well as to put it a little bit into context of some of the broader research. And as we move through either during the presentation or at the end, I'd really like to see, as well as hear your insights into how this relates to what you do in your practice every day. We're at a stage in our research, we've done a number of fundamental studies and are starting to move into more applied work, and this is where the connections with you folks is really critical to make sure that the work continues to be useful. So this is the general outline for the presentation. We're going to start with my theoretical perspective that drives and organizes how our experiments run. A few terms and definitions so that we're using the same definitions as we go through. And then I've organized some examples from work in our lab, as well as I said, touching on how it fits into some of the broader context in terms of visual cues, auditory cues, as well as tactile and proprioceptive input. And this all goes to my broader interest in perceptual motor integration. And I very specifically use the term perceptual motor integration because sensory information can be equal for different people, but how they use it being very different. One of my examples from my own life is my mom and I continually argue over the color purple and blue. And there's a certain range where we have agreed to disagree that one is blue and one is purple. And although the actual light that we're perceiving is from a sensory perspective the same, the way that we perceive it is different. And so there are many classic examples in psychology, one here being, do you see the face, the two faces or the vase? And so we always need to think about how people are interpreting the information as well as the sensory information that's available. So I use an information processing model when I'm thinking about how people move in their environment. This is where I say sticking to recording is a bit tricky for me, so we're color-coded, so we should be okay. If we start with the eye, we identify a goal in our environment. So it might be, I'm thirsty, so I identify where my mug is, and use that information to determine what my goal is. And then our brain helps organize what needs to be done to achieve that goal. And there will be a number of different things that need to be done. But eventually we'll get to a movement plan that is then sent down through the brainstem to the spinal cord, and the appropriate muscles are activated. And so we can perform that movement. But along with that, there are a number of other parallel networks that are providing input and feedback about how we're moving. So in our yellow areas, two of the primary sources of feedback are feedback from our tactile and proprioceptive system, so information about how our body is moving, as well as the visual feedback. So as I reach towards my cup, I can see where my hand is relative to the cup. And I take that feedback information and I compare that to what my goal or my intent was, and I can make adjustments to that movement. And that's the green arrow going back to the brain in terms of processing where my goal is compared to where my limb is, sorry, compared to what my goal is, and making adjustments so I can achieve my goal. And much of what we do as infants is move in our environment and learn how to make those adaptations. So as think about infants' early reaches, is you can visibly see what I need motion capture systems or motion analysis systems to see in adults. You can see with infants their hand actually making those corrections. Now, the thing that I find really interesting about movement is that to do it well, you can't think about it. As soon as you consciously think about it, you've actually disrupted the pathways that you should be using. And so the challenge for us as instructors and therapists is to think about how to get people to practice so that they're using those non-conscious pathways as opposed to using the conscious pathways that they might need initially, but eventually we want to get to that non-conscious processing. I also use an ecological perspective, and you don't always see these all pulled together. This is a bit of a reflection of my view on the world. And the ecological perspective considers the task, the environment, as well as the individual, and considers how those come together to create a unique movement situation. So you need to adapt the task and the environment to suit the individual characteristics. So when you're doing assessments, you're determining who is this person, how are they moving in the environment, and then you're making decisions all the time about what the tasks should be to help facilitate the movements you want to see. So this creates a model for how we think about creating instructional environments. So we'll talk a lot about reaching today. I just wanted to give you a little bit of information about why we use reaching in the lab. It is an everyday action that is needed for communication, for self-care, for mobility. It is also one of the primary goal-directed movements. So when we have a goal in mind, then we reach towards something to achieve that goal, whether it's pressing a button or interacting with an object. And for those living with a disability, reaching is even more important. It's often necessary for communication, for just moving around a building to be able to hit the different buttons. And so this is really important for functional independence. So our goal in the Perceptual Motor Integration Lab is to think about how we can change the sensory input to help improve reaching performance. And how does that look? What does that look like for different individuals? And I'm also very interested in not just if something works, but finding out how and why it works. And the reason I'm so interested in how and why it works is because when you're working with individuals, each individual is unique. And it's good to know that globally something works, but each individual is just that, an individual. And so if we understand how and why different intervention techniques work, that can help you as therapists make better decisions about what to try first, or if the technique that you start with, because that's what broadly the evidence tells us doesn't work, what's the next option? And so by understanding how and why, you can connect those assessments with the treatment decisions. So just a few terms and definitions. that I'll be using more from the behavior field, but certainly comes up in physiotherapy and occupational therapy. Augmented, alternative, and intrinsic feedback. So I'll start with intrinsic feedback. I'm defining that as any feedback that is available to you in the environment that you normally perform the task. And so if it's normally available to you, then it's intrinsic. Augmented feedback, I'm defining as any feedback that is normally available, but now we've augmented somehow. So it might be by providing a mirror. So normally I have visual feedback of my limb, but if I can look into a mirror, now I've augmented how much visual feedback I have. And I'm defining alternative feedback as a sensory input that is not typically or necessarily inherent to the task, but instead can be added. So the example that we'll see in the next section is looking at different kinds of auditory stimuli. They're not necessary for the task, but they contribute to how we perform them. Two of the primary measures or dependent variables that I'll be sharing with you today are reaction time and movement time. And these are broadly defined as performance variables. And the reason that we're interested in these is because reaction time is a measure of how long it takes you to plan movement. So we take a start time as when you either received a goal signal or made the decision to move. And then once that movement is actually begun or initiated, that is defined as the reaction time, how long it took you to react. Movement time is the time it takes you to actually execute the movement. So from that movement initiation until the movement is completed. Now, during movement execution, there's also a lot of opportunity to make corrections to our movement. So while we're executing the movement, the adjustments and planning for future movements isn't over. So there's a number of parallel processes going on that we're trying to unpack. They also, being performance variables, give us some indication about how efficient the movements are for people. And so if things become faster, more efficient, then that also has an effect on how fatigued that activity makes them. So meaning they can have more time then for other activities throughout their day. And movement trajectories. So a lot of our research involves motion capture. So it's not unlike the Connect system. The Connect system is actually based on our research motion capture systems. And it's really no different other than it's not as spatially accurate as our system. So we use the motion capture system because we can really get in and see things that we can't see with our naked eye. And so just to orient you a bit to this graph, at the top we have the actual movement displacement, so how the limb moved through the air, so actually how the finger tracked through the air and back. Just going to point for a second.
So we can see this is where they started. They were stationary. That green point represents when they started to move. We can see they moved, then they stayed on the goal, and then this is actually the return movement back.
So by looking at that movement from start to finish, we can then use a number of computer programs to extract other information about the movements. So we use this motion capture system to find reaction time and movement time for some of our experiments. Other experiments we use a key, not like a keyboard, but just that's a little bit more accurate. And another measure I wanted to just point out is peak velocity. So peak velocity in that second graph down is that blue dot. So that's the fastest that you've moved throughout the movement. So it's the peak speed during the movement. And typically when we're thinking about these goal-directed reaching movements, anything that happens after peak velocity represents time where we're actually implementing corrections. So we can't quite see that here, but what happens after peak velocity is that we start to make corrections based on the feedback that we picked up in the beginning of the movement. Okay. So we'll move on and start talking about some of the benefits of the visual cues. I'd just like to highlight that I'm really scratching the surface when it comes to visual feedback. There is a large, we could do a whole course on visual feedback for movement. So I'm going to highlight a few things from my own research program, and then at the end connect to a few other examples in the literature for us to think about how that applies. So I wanted to talk a little bit about movement planning in autism, and I likely presented this experiment when I first arrived in 2010 as well. But I wanted to bring it back again because it's going to connect again to some of our current research that we've been doing. So this experiment was based on seminal work done by David Rosenbaum that showed that if we give advanced information to people, they can make choices about where they're going to move, and they can initiate their movement faster. And that's not terribly surprising, but what was very consistent that he showed is that it's not just any information, there's specific information that helps us plan our movements more easily. And so if you have information about which hand or which limb you're going to perform the movement with, then that is much more beneficial than knowing the direction. And it makes sense if you think about planning and organizing in the brain. If you can plan and prepare to move with your right hand, then you can consolidate that planning activity to the left hemisphere. He also showed that knowing what direction you're going to move is more beneficial than knowing how far. Okay. And so at this point, we were really interested in this kind of paradigm because there had been a few experiments that had suggested that individuals with autism have a hard time planning their movements specifically. But a lot of that work had been based on giving people verbal instructions about how they were going to perform their movements. And so we wanted to see if we took a task and gave very direct visual information, if then movement planning would become easier. This is also something that's important to think about in my other application realm of my life, is in terms of thinking about the design and application of automobiles and other transportation vehicles. The more direct information we give people, the more quickly they can prepare their movements in advance. And so that thinking about that organization is really helpful. And so in this task, those white buttons represented the home position for the left and right finger. And each hand had 4 possible buttons. And so if we provided a cue for the left hand, we would light up all 4 buttons for the left hand. They'd turn off, and then one of them would light up. And so someone could then move to that one target as quickly and accurately as they could. The most important result from this was that individuals with autism were using that direct information. We can see that overall, that group on the right, it takes longer to plan the movements, and so it takes longer to initiate the movements. But the pattern of the bars is the same. So we can notice the first green arrow, when we give information about the hand, there is a clear and significant improvement in how quickly they can initiate their movement. Interestingly, as well, that blue arrow highlights the last, I guess it's looking turquoise here. Sure, that last turquoise bar. So this is a trial where one light comes on, turns off, and then comes back on, and you have to move to it. And so you know exactly where you have to go. You just have to wait for that go signal. And we can see that the people with autism respond very quickly, as we would expect. And the people with autism also respond the fastest in that condition. So they are using all the information, but it still takes a while to organize that information. So processing the visual information takes some time, although they are doing it. So that's a really important piece when we're thinking about how we're going to provide information. This next experiment looks more at the movement execution point. The movement execution part of the movement. And so participants had their finger on a center position, and they would either have to move to the left or to the right. And we use these really fun, what we call visual inclusion models. I've discovered from my own children that they also think they're super cool. They always want to go and stop when we go to swimming lessons. They always want to stop at the lab so they can try on the cool glasses. So the way the glasses work, we can see that's the actual developer wearing them. When there's a current running through them, they're transparent, you can see through them, but then we can drop that current, and within 2 milliseconds, they turn opaque, and you can't see your environment. And so it really helps us be able to change how much feedback and when people have feedback. And so we use those goggles so that once somebody started moving, they couldn't see where they were moving anymore. And we use the OptiTrack. So you can see just on the tip of the finger, we use these little, what are called iREDs. They're just a little circle that emits infrared like a remote control would. And the position sensors, which are just like the Connect, track exactly where that circle is, and that's how we are able to develop those movement trajectories. And so with these movement trajectories, we get people to do the movements a few times, because one of the things that is an example of being more proficient or better at a skill is being able to do it consistently. So I always say, I can get a strike once in a bowling game, and I can pretty much count on that, but I'm certainly not getting 10. And so it's that consistency of performance that is also important. And so these trajectories really represent that consistency. So we expect the variability to go up as you're moving, because whatever variability is present early in the movement continues to accumulate, or that error continues to accumulate until your nervous system does something about it and makes a correction. And so that dramatic drop at the end is a clear indication that you made corrections to your movement in order to hit the target. So a few things here. One is that both groups are hitting the target with just as much accuracy. So that's really good. The group with autism arguably has a much harder job because they have more variability, or think about it as more noise in the movement from trial to trial that they're having to contend and correct with. But they are correcting that variability, so that's really important. And when we compare the trials with and without vision, the tasks, because they were buttons about that big and you stuck up, you could really feel and find them. The participants without autism, it didn't matter too much if they had feedback, visual feedback or not. They could reproduce the movement and find the target with just as much speed of execution. So that's that moment time we talked about. For participants with autism, though, they took longer when vision was present. That's not uncommon, because if we're using the visual feedback, it takes time to use the visual feedback. And so this is further evidence that they are using visual feedback, but it takes more time to do that. The last piece here is, though, that everybody was just as accurate without vision. And so the other way to look at this is that using the visual information causes more time and cost and energy to implement that feedback. So this is like a really tiny sliver of looking at visual feedback, but I just wanted to connect it back to some other things in the broader world, really. So just starting on the right from being kids, we love to look in a mirror. We love to see how we're moving. I'm a dancer, and we love to look in the mirror even though we know we shouldn't, because then we can see how we're moving, we can get feedback about that. And in fact, going back to that earlier description, seeing movement is often a more accurate representation than trying to provide verbal instruction for movement, because there's a lot of information that our brain is processing without our conscious awareness. So there's definitely value to seeing that. And the mirror box is an example of a growing technique that's used to augment and provide different visual feedback. So I'm sure many of you are familiar with this, but just to briefly summarize, somebody can put either their less or paretic hand, often for stroke, or if someone's had an amputation, they can put the more involved hand inside the box, and then they put their other hand on the other side, and they attempt to perform bilateral movements together. And what happens is your brain sees that right hand moving, even if it's not moving as much. And so it's augmenting and actually changing the visual feedback and providing some different sensory inputs to the brain. So going back to our earlier model, it's providing new sensory feedback for the brain to then think about the movements. And so there's definitely mixed reports in the literature, but I would say that there is more evidence for using it for stroke and complex regional pain syndrome following amputation. It's certainly, I'd love to hear anybody's experiences here. When I've talked to other clinicians, they've said it works wonders for some people and for some people not at all. And I think that really reflects that individual variability that we were talking about earlier. The other here, I have a picture of the weight trainer. as a reminder about a concept known as specificity of learning. And so going back to what we were talking about in terms of it's not just the motor movements, but it's the perception of our moving limbs in the environment that really becomes a whole part. So I like to think about it as not motor memories, but perceptual motor memories, because we remember how we perceive that movement. And so there's been a lot of work done with specificity of learning, but more in athletic and these basic lab tasks, showing that the more you practice with visual feedback, the more that visual input becomes part of that overall motor memory. So that if you take it away, now there's a bigger cost to it. And so one representative, Trajectories and Premotor, they showed with powerlifters that the more they practiced in front of the mirror, the more they depended on the mirror because it became part of that overall motor memory. So when we're thinking in applied settings, the mirror is certainly really valuable for providing some of that augmented feedback, but we're still not sure about how much and when and how to use it specifically. Yes, absolutely.
And I've seen that work really nicely with some children with autism, where you're working on a program in front of the mirror, and for a variety of reasons, they're more interested in doing the activity, feedback, etc.
Exactly. Yeah. No, I think that's a really interesting area to think about, because the first goal is we want kids and adults moving, and so that's step one. And if that's the motivator to get moving, then absolutely. That's really helpful. And it could also be because that feedback is more novel to them. And so it's really interesting for them to try to understand how the moving body learns. They're learning a lot about movement. And I think that's where we still don't know a lot about how to apply some of these principles, because this is a different case than the lab environments.
Cheryl, when anyone makes a comment or question, if you can
repeat it. So the comment or question I was just responding to is about using the mirror as a motivator, in particular for children with autism. So it's a dancer, it's also a motivator. So just to summarize, we've very much scratched the surface in this area. But I would say visual feedback improves movement accuracy, but maybe more challenging for some individuals to process. And I think I would update that now, as it can also provide motivation to move in the environment. So mirrors are really handy and can be used in different ways. And I think we're still learning about how that can be used. There's a whole other body of literature I haven't really touched on, but if anybody's interested, I'm happy to share different references looking at observational learning and how we can use, for example, peer models who move closer to how the children are moving, to give them, again, that visual information about how to move that can be really beneficial.
I just have a comment on that. I often, when my kids I work with are like walking and they start daycare, sometimes we see it first in their motivation.
Yeah, so Maria was just saying she often sees a boost in the late walkers once they get to daycare. They see the other kids walking and they've got those peer models, and that really helps to encourage them to get going. Okay, so I think there was a holding here. I think we lost a little in our transition, but that's okay. So just as we're following on, we're going to move on to some benefits of auditory cues. So I'm interested to hear Kelly's perspective on this. So this question, I want to start with what I consider to be some of the seminal work by Michael Poe, considering how rhythmic auditory stimuli, which is really just a researcher's way of saying a metronome or a beat, how does that improve movement quality for individuals post-stroke? So this was work that we did in our lab, but they looked at the same kinds of reaching movements, but this one was going back and forth. So we call that a reciprocal reaching movement, with and without an auditory stimulus. And briefly, what they found was that when that rhythmic auditory stimulus was present, there was reduced variability as well as smoother kinematics. So starting with the timing variability, this very much makes sense and fits with basic psychological research in that auditory information is our preferred source of information for timing. So it makes sense by adding that auditory information that would then help with the timing of the movements. We also see smoother kinematics. So on the left are movement trajectories with an auditory stimulus, and then on the right are movement trajectories without an auditory stimulus. So you can see in many cases these large corrections that look not unlike infants reaching, and then when the rhythmic auditory stimulus is present, they smooth out quite a bit. So this was some original work done in 2002. And more recently, Johansson et al. In 2014 looked at this for children with cerebral palsy. And so their question was, does a 4-week upper limb metronome training program improve motor quality in children with cerebral palsy? So participants moved through a series of button pressing tasks. I'm always amazed at how many different ways we can find to press buttons. We seem to find a lot. And they also did this kind of trajectory analysis of the reaching movements pre and post intervention. And so their results showed overall improvements in the quality of the reaching movements once again. And they looked at case by case, and some participants maintained these performance gains even in the retention phase, so even after they hadn't been practicing with that rhythmic auditory stimulus. So when we think about that specificity of learning, when that rhythmic auditory stimulus was taken away, they were still moving. And so their graphs are not quite as clear to see in terms of from a presentation standpoint, but what I hope you can see is that in the bottom graph, the black line there, the black line, when their rhythmic auditory stimulus, they've been practicing with it, their reach trajectory is much further and much smoother compared to pre-training. So we've become quite interested in this idea in our lab, and thinking about, do rhythmic auditory stimuli facilitate movement planning, movement execution, or both? And in part why we're interested in this is there's a number of motivating, fun, and low-cost opportunities to provide music programming as well as dance programming. And there are many programs that exist both in Winnipeg and around the world already. But our goal was to understand how and why that might work. And so some other work done by Hadfield and colleagues down in the States with university students showed that when you're moving back and forth to the two targets, that again, the performance improved, and the results suggested that it may be related to movement planning. So we wanted to explore that more specifically, as well as in a clinical population. So this first experiment, some of you may know Jackie Lagwig. She's been in Winnipeg for a number of decades and does some of the explorability programming at the Roe Winnipeg Valley School, and I think has done some other programming, or I know she does some other programming around the city. And so this was her master's experiment, and she developed this reaching apparatus. And what was unique about it, think about how we were going to develop this from an experimental standpoint, is that we needed to be able to create different distances or amplitudes for the target. We were working with adults with cerebral palsy, and not everybody was going to be able to reach the same distance. So those white lines that you see, she created tracks so that we could quickly and easily establish what was a functional and comfortable reach for somebody and adjust the targets there. Another adaptation we had to make that we hadn't done in our lab previously was to have more markers and options for markers. So she created a very comfortable sleeve that went on the wrist, and we had a number of Velcro points so that we could find the best location to put the markers regardless of how somebody wanted to reach out and touch the buttons. And so the different conditions that she did was she had a no sound condition where just one of the targets would light up and somebody had to move and touch the target. She had a sound before condition where participants heard 3 beats, and we picked the duration between the beats as 3 seconds based on pilot work we had done in the lab. And then the sound during, the target would light up and then the sound would start once participants were moving. And so we wanted to clearly separate these 2 different conditions. And so when we look at movement planning, because we moved and varied the target distances, we used the no sound condition as our baseline and then looked to see how people perform relative to their own baseline. Okay, so you see we only have 2 conditions presented here because in order to get the blue bars, we took the sound before condition and subtracted the no sound condition. And so the fact that those numbers are negative means that when you have a sound before you start moving, you're able to plan and initiate your movement more quickly. And again, that's not surprising when you have that preparation. You think about before a race, you hear the beep, beep, you can prepare to move before you start going. Although they didn't know which target they were going to go to until it actually happened. But the beeps seem to help to focus them on the target area and being ready to move. And then we can see that when the beeping didn't start till after they started moving, they were much slower to initiate. And again, this isn't surprising. Having a sound present when you start a movement helps you to begin it faster. But what we saw was the same pattern for both the adults with cerebral palsy as well as the university students. And so this tells us that the rhythmic auditory stimulus can help the adults with CP be able to initiate their movements more quickly. And this measure here, this relative time to peak velocity, this is taking how much time you spent before that peak velocity marker and comparing it to how much time you spent after. And that gives us a ratio that tells us about how much time you spent performing corrections to your movement versus how much of your time you just executed the plan. And so for the typically developing participants, you can see when the sound was present during the movement, they spent a lot more time in that correction phase approaching the target. And for the group with cerebral palsy, there were no significant differences, but there was a trend towards the sound before condition, leading them to having spending more time in that online correction phase. And there were no differences in the variable error, so in how accurately people were pressing the buttons. And so what we can say from this first experiment is that providing the sound while people are planning their movements, it will help facilitate the movement in terms of being faster without any cost to the accuracy. Because usually when we move faster, we tend to be less accurate. This work is currently being followed up by current master's student Carrie Peters. And she's interested in this: does the benefit of the rhythmic auditory stimuli increase when other sources of sensory input are reduced? So our thinking here is that if your proprioceptive information is maybe not as accurate, or your visual feedback is not as accurate or more difficult to use, that providing that rhythm may actually be more beneficial. And so she's created some adaptations to the apparatus. You can see she was preparing to do the work with people with cerebral palsy again, but we're just getting going with that. And so she's created those black tracks along the screen. And she's created some new buttons that are a little bit more durable and that light up themselves. So it's that gradual improvement of our different apparatuses. And so this is data from a group of university students. And what we're seeing overall is that providing the sound before, or she added a sound throughout conditions so that the metronome continues from before all the way to during the movement. That during those tasks, you initiate your movements the most quickly compared to the no sound condition. But there's no, at this point, interaction between the vision and no vision in different sound conditions. And when we look at the error scores for this one, what we see is that, oh no, you can't see that. When we have visual information, it doesn't matter if you have the sound or not. And that's not surprising because that visual feedback would be that preferred source of feedback for spatial information. But what's interesting is we tend to undershoot or stop short of the target when we don't have any sound. And that's exactly what we would expect from decades of research. But in the sound before and sound throughout condition, the participants tend to move a little bit further relative to the no sound condition. So their accuracy is slightly better when they have the sound presented either before or throughout the movement. Kayla is a graduate of my lab who also did some work with children looking at implicit motor sequence learning. And so she was interested in does the combined audiovisual information, is that more or less helpful for children? So she had a group of 7 to 9-year-olds as well as young adults, and she was looking at a 10-item repeating sequence. And what makes this implicit motor learning is we don't tell participants that they're learning a sequence. Their job is to move and practice. So I'll just skip forward for a second. So we used animals and animal sounds. And so your job during this task is, if the cat lights up, is to press the key that responds to the cat. If the duck appears, press the corresponding key, and so on. And so participants were asked to sit down and follow along with the computer, and they would repeat that over a series of trials as they were moving. And one group would do this with just the pictures, and the other group would also have a sound each time the picture was presented. And so they did this 10-item repeating sequence with or without those accompanying sounds. And the experimental design looks like this. And so with learning studies, we have to have a period of practice. So that's that day 1 acquisition. So they performed, I believe it was 8 blocks of these trials, pressing the animals as they go. And then they did another block that was a random sequence. And so with the random sequence, we've now taken out that pattern, and we look to see if now you're slower again because it's not the sequence you've been practicing. We then have you redo that 10-item repeating sequence, and that's known as retention, because we want to see if you retain what you've learned. And then we had people come back on day 2 and perform a series of different trials, looking at performing the skill in the other conditions. So if you practice with sound, practicing without the sound. And we also did what we call a motor skill recall. So in this particular one, they just heard the sounds, and they had to try to perform the sequence just by hearing the sounds, but no longer having that visual information. So it was a bit of a harder test. And then we did an explicit awareness test to ask if people were aware there was a repeating sequence. The good thing about these tasks, and they've been used quite a lot in literature, is that most people aren't aware, and even if they are aware, it doesn't seem to change the results, but we do always check for that. So when we look at reaction time for this group, on the bottom are the adults, and we can see the first line is the acquisition phase. And the adults, this was a pretty easy task. And so we didn't actually see a lot of learning for the adults because they were following along and it wasn't too difficult. For the children, we can see that drop from the first point to the second point represents they're starting to learn that sequence. And then the 2 points towards the side, we can see that they actually got better from day 1 to day 2. And this isn't uncommon. This can be termed sleep consolidation. So they've gone home and slept, and then they've been able to consolidate what they practiced and actually perform better the next day. There's certainly also potential attentional factors. By the time they're coming back, they're fresh the second day as opposed to having completed all of these trials ahead of time. When we looked at the motor skill recall, this was an interesting one for me in terms of the visual condition. If the group, so the visual condition here represents the group that practiced with just the images. And so the group that practiced just with the images, when they had to perform the motor skill recall with the sound, it had no impact for the adults. The adults were able to transfer what they had practiced with just the pictures to the sounds they were hearing quite effectively. And for the children, on the other hand, we can see that large increase in the reaction times. When they had to transfer to that just sound condition, that was a lot harder for them. But in the audiovisual condition, if the children practiced with the sound, then they transferred quite nicely to without sound. So the kids had more difficulty crossing the different modalities, so moving from visual to auditory, whereas if they practiced with the auditory, they were quite capable of performing well, even though the visual information wasn't present. So overall, we're seeing that auditory cues can facilitate movement preparation. And I think that in turn, we're seeing improvements in movement execution. And so the statement's based on a bit of a larger look at the different variables that we collect. But I think from what we're seeing is that The rhythmic auditory stimulus helps to create a more stable plan that then means fewer corrections need to be made, and then when the corrections are made, they're more effective. And so where we're going with some of this work, we've been partnering with the Royal Winnipeg Ballet School. This is through Jackie Ladwig and her work with explorability, and looking at the movement performance of these kinds of rhythmical upper limb movements that I've been talking about, but also looking at the benefits of practicing with rhythm and dance on a regular basis that seems that potentially transfers to the balance as well as different mobility tasks. And from some of our early pilot work, it seems that it's regardless of whether it's intellectual or physical challenges that somebody's having or a combination, that we see improvements with these goal-directed movements across the board. When we're talking about balance and mobility, it seems the improvements were more specific to the adults with a physical disability specifically. So we're still early in the work, and it's a really exciting partnership because we're seeing the use of this rhythm in practice, and we can connect in some of the ideas of motivation. Some of the newer learning periods with this optimal period by Gabby Wolf, talking about how motivation interacts with our practice, which then leads to differences in how we perform the movements in the long run. Okay, so the last one, the benefits of tactile and proprioceptive input. So this research really came out of some of that earlier work that I was talking about with the individuals with autism, as well as some work that's done at the Kennedy Krieger Institute in Baltimore. And so taken together, I saw that visual input was really helpful in the direct visual for individuals with autism, and that they were using visual feedback, but it seemed to be more challenging. They had also shown with different types of tasks a preference for proprioceptive feedback. And from a neurological standpoint, the somatosensory and motor cortices are right beside each other, so easy, quote unquote, easy communication, whereas the visual networks have to travel a much further distance and require more integration. And so we wanted to know, what is the effect of the addition of tactile feedback have on movement control when that visual feedback is present? And I also wondered if it had to do with movement complexity. And so what I mean by that, and what the task was, is that on the right, if you can see that board, I'm not sure if you can make it, there's sort of a line in the middle of the board. And we used, not me personally, somebody from architecture used a laser. I would like to use a laser. Used a laser to create this groove so that participants could slide their finger. And when we were looking across different tasks, a lot of people had used sliding tasks where you had this extra tactile feedback. But it's also, you only need to control 2 degrees of freedom if you're sliding on the table, as opposed to moving through the air, where now I have to control 6 degrees of freedom. So we've got a few different things to consider here, both in terms of feedback and movement complexity. And so this was worked out by my first master's student, Ren, and he did this with both EMG and motion analysis. And that was because we also wanted to take that reaction time variable and separate it out into the time needed to plan the movement, and then the time it takes for the muscle to generate enough activity to initiate the limb. So I'll explain that more in just a moment. The task that he used was all underneath this board, so participants couldn't actually see any of these points. But what would happen was a light would light up, so we'd have the start position light up, and somebody would put their finger on that light. And then the fixation light would appear, and then after a random period of time, it would disappear, and one of the 2 targets would appear. And we grouped the trials together, so then in some trials, they were asked to slide their finger along that groove. And we had another board that didn't have a groove, that then they were slid. And in the third condition, now they had to lift and actually move through the air. So the nice thing about this task design is that all of them are the same, other than how much feedback or how much complexity they need to control. And so this is a look at premotor reaction time. So premotor reaction time we use the EMG to figure out. And so what happens is we take the time that the light turned on until we see the first activity in that electrode on the muscles. And that's known as the premotor reaction time. And that's thought to represent the time it takes you to identify the stimulus, process the information, and send the signal to the muscle, but not the time it takes you to activate the muscle. And so for the typically developing participants, for the 1D and 2D movements, as we call them, the sliding movements, those took actually more time to prepare than reaching through the air. And so at first I was like, there's more complexity in reaching through the air. I would have thought that time. And then we thought about it some more, and that reaching through the air is what we do all day, every day. When we brush our teeth, when we get a cup, this is the movements that we do. Maybe the next generation will be different, but most of us adults don't spend as much time sliding. And so these sliding movements aren't as used, and so perhaps took a bit more time to then prepare. Now, for the participants with autism who were age-matched to our typically developing participants, it didn't make a difference, actually. So the sliding movements took just as much time to prepare as those 3D movements. So this was interesting, but in order to get the picture, we need to put a few different variables together to try to see what's going on, and then usually lots of experiments and lots of labs before we can say much. This variable looks at how much time you spent after peak velocity. And we said that was the time that you were making corrections based on that feedback. And we can see for the 3D movements, for the participants with autism, they were there, that they spent a lot more time after peak velocity, specifically in those 3D movements. Again, suggesting that they are using the visual feedback, but it takes more time, and I would argue more effort to use that visual feedback compared to the sliding. So they're just as good at those sliding movements, but the 3D movements, they're just as accurate, which is excellent, but it takes longer to achieve that same accuracy, and it's specific to those 3D movements. So we're still, from this, can't clearly say whether it's the complexity of their feedback, and arguably you can't completely separate those two. There's some different things we'd like to do to try to look at that. Oops. But we'll still need some more time to do that. Okay, last experiment, our final example. This is my current PhD student, Nisha, but this is her master's work that I'll be presenting. And so this was based on a bike that was developed in the Faculty of Engineering at the University of Manitoba. And we did this work in collaboration with Zara Musavi. It was one of her former students that developed the bike. And then a lot of collaboration with Katinka Stasina from the Songbird Research Center in terms of some of the neurophysiological methods. So the questions for this one was, what are the immediate effects for this Mechano-sensory rehabilitation bicycle on the neurological network? So again, trying to understand the why behind the improvements that we see. And are there effects of training with this bicycle on balance and walking performance, specifically for individuals with incomplete spinal cord injuries? And so I'll just show you. Oh, this is the part that I should have checked before. Okay. Oh, there's a button. Oh. Okay, that's okay. I can describe. You can see. We all know what bicycles do. So they go around. So the person is in supine, and it's actually passive cycling, which is interesting. And so it's passive cycling, and on the bottom is this solenoid that provides tapping to the fifth metatarsal. And the logic behind this bike was based on some work done by some NASA scientists, where having this tapping on the bottom of the foot was supposed to help recreate some of the weight bearing that you would normally achieve, and again provide some alternative sensory input to the brain that would simulate that kind of weight bearing. But this is very pilot work, and there is a lot of more questions than answers that come out of it, but there's some interesting distinctions that we see. So the bike goes goes around. Oops. And then we can turn the tapping on or turn the tapping off. And so I'll just present both the neurological assessment and then a little bit of the more functional assessments. So for the H reflex assessment, we did this randomized, where one session they would come in and they would perform it without the tapping and one with the tapping. And we can actually also do this with healthy young adults. That data, we're still collecting some more data to better understand the mechanisms of the bike with and without the tapping, so that we at this point have more questions than answers. The data I'm going to present today is from some participants with incomplete spinal cord injuries. And so they came in for either their first or second session. We did an H reflex assessment, and then we did 30 minutes of training with the cycling, either with or without the mechanical stimulation, and then we repeated the H reflex assessment. So for the H reflex assessment what we did is we calculated the H reflexes at different, what we call interstimulus intervals. And so we're looking at how much inhibition there is of that second H reflex. And so we have 45, 55, 70, 100, and 200, because the different times help us understand where in the nervous system the effect is happening. So if we see the effects at 45 and 55, that needs to be spinal cord changes because it's too fast to involve the cortex. If we start to see changes at 100 or 200, that suggests that it involved cortical networks. So this is the result of just 4 cases. So I said very preliminary and data. But what we saw across a number of the different measures, I'm just highlighting one here, is that it mattered whether they had spasticity or not. And so this is organized in terms of having a modified Ashworth scale of 2 or a modified Ashworth scale of 0. And broadly speaking, when the bars go up, that's the good thing. We want the bars to go up. When the bars go up, the improved inhibition was specific to the people with spasticity. So across the measures, it seemed that if somebody didn't have spasticity, the bike was not having a huge impact. But if they had spasticity, there was more evidence. Again, this is only 2 cases, so we have to take that for what it is. But those specifically were the people who started to see some benefits. So this is important preliminary kind of pilot data because it helps us understand that we really need to consider the spasticity when we're thinking about our different groups and how that might impact. So going to this idea that it's the assessment, not necessarily the diagnosis. For the training data, we did baseline measurements, did 4 weeks of training 3 times a week for 30 minutes with the bicycle, a mid-evaluation session, another 4 weeks of training, post-evaluation, and then 8 weeks of rest, followed by post-training follow-up. So I just have 3 cases to present here, because you can imagine coming into the Health Sciences Center 3 times a week for this many weeks, not everybody can do, so some people volunteered just for the short-term study. And I've laid all the numbers out here because with case data, I think it better represents what we're seeing so we can see for what it is. So we've got case 1, case 2, and case 3. And data I've selected for today is the Burke balance scale, the 6-minute walk test, and the 10-meter walk test. And so we can see that with the Burke balance scale, we're seeing some improvement for case 1. Some improvement, but already balance being reasonably strong in this case 2. And then not a lot of change in case 3. So often when we're dealing with smaller cases, this is the reality of what we see and what you see in clinic as well, I'm sure. What we see with the 6-minute walk test, again, for this participant, not a lot of change, although some improvement to the end of the session. For case 2, we see improvement from baseline, even though there's a drop on the second one. So improvement that continues on. And again, not as clear with this one, we see quite a bit of improvement, but when the training stops, now we see a decrease. So there's a lot of variability that we didn't track here was, for example, did they keep up with more physical activity once the training stopped? Some people commented that they felt better, and so they started doing more. So my guess is that that's what we're seeing in case 2. And the 10-meter walk test, again, we're seeing walk times go down here, so we're seeing some improvement. So again, very early data, and there are a number of different approaches to this. I think we still need a lot more work to figure out whether the tapping is beneficial on top of the cycling. And then there's a lot of questions about what should that tapping be. Should it be heel-toe? Should it be timed with the step? Right now, it was just going at 1 hertz because that's what the only other study had done. And so there's still a lot of questions about exactly what that stimulus can and should be. So overall, I think additional tactile feedback will hinder movement control depending on individual characteristics. And that's the her key point I really see this is it depends on the individual characteristics. And so we really need to think about who that person is and how they want to move. Some of the places I'd like to see this moving, we've started working more closely with Roe, Eating Resources Our Way here in Winnipeg. And thinking about how we present information when we're learning different life skills such as cooking. How that direct visual information can be really helpful, but also how we're providing some of that input in terms of learning those different skills. So using that hand over hand to give somebody that feeling of what it is like to perform that coordination pattern, as opposed to visually just demonstrating what it is. And thinking about who that person is and what is the instructional technique that's going to best suit how they want to get information. Another exciting initiative is Jackie Patch from the College of Rehabilitation Sciences and Occupational Therapy invited me to work with her in Freedom Concepts to start investigating some of the adaptive bicycles. So we're looking towards getting some of that work going in the next year. So again, bicycles being an example of providing lots of rhythmical proprioceptive information while you're cycling that gives information to the nervous system about this is how I move my limbs in an alternate fashion. And there's all sorts of questions about the types of proprioceptive information, visual feedback, auditory feedback. We don't want to overwhelm people, but we want to provide the feedback that's most helpful. So just bringing it back to the beginning, use this model a lot also in my classes and hoping that the students make it to you, thinking about how they can adapt different tasks depending on the individual. I think in this room, you already think this way, even if you don't put this specific model name to it. But really thinking about who is the individual that I'm working with, and what is their environment, what aspects of their environment can we change, and what aspects of their environment maybe we can't change but are contributing to how that person moves. And then thinking about the tasks, so that's really where we have the most control, is thinking about the tasks and the practice opportunities, how we can mold those to help somebody improve their motor skills at school, at home, recreation, and at work. And so just tying back into this model is I really think about as we're practicing, as I said, that we're learning these memories not just about how our limbs move, but really about the sensory information that we're expecting to get, and then being able to use that sensory input. And so being able to use it means being able to perceive it. And so we still have some questions about when, how long we should use different alternative and augmented sources of feedback. And it for sure depends on who the person is, what those individual motivators are. But in the end, we want to develop really efficient highways. I always think about these neural pathways as highways. We want them to be really efficient, but we want them to be flexible. We don't want a highway that if that one highway stops, everything stops. So we want to have different options available, but we want to practice so that those highways the information can move and without having to consciously think about each step. So I'd like to thank all of my students and collaborators. I certainly do none of this work alone and couldn't do it without all their help and input and insight. I'd like to specifically thank the students whose work we've highlighted today, Kayla, Jackie, Carrie, Nisha, and Graham, as well as the funding agencies and participants, again, we would definitely not be able to do this research. So, any questions? Oh, so webinar folks, if you have any questions, you can type them in.
So I guess this is what you worry about, you get very specific questions. Anyway, I work with amputees.
Okay.
I work with congenital amputees and with traumatic amputees.
Okay.
And so I'm working with some myoelectric prosthetics on a limb that has never had any motor development. And I'm trying to teach, you know, flexion, extension, to operate a myoelectric signal. So, it's hard. You know, they co-contract a lot.
Yes. Yeah.
And, you know, do you have anything to say about that kind of thing? That for you, that's tactile. I use tactile, I use visual, I use mirrors, I use everything I can think of, and it's still, because they don't have anything laid down.
Yeah, I think that is really extremely, oh, sorry, repeat the question. So I get to summarize, so you can tell me if I have it correct. So the question is related to working with both traumatic amputees and congenital amputees, and working with myoelectric prosthetics, hands specifically, and how difficult that can be to try to teach. And then there's a lot of co-contraction in learning, and then to use tactile feedback, mirrors, everything that you can think of. Yeah, I think that is a really interesting area, and is becoming, there's not a lot of research on it because it's so new, and the devices are still so new. There's some interesting work, I believe it's Scott Fry out of the States, I want to say Oregon, looking at hand transplants and some of the motor control that goes with that. But definitely the congenital and then traumatic would be very different in terms of how the brain developed and the organization. We do know, for example, when we look at congenital blindness versus acquired blindness, that the motor patterns we see are also different. We have this, I think it's really interesting. I think one of the ideas that I would think about is providing some feedback that is dependent on how they move, for example, so getting indications that they've achieved a goal. So some variations I've seen that there's different video games that will respond to small amounts of movement. There are different kinds of biofeedback, because what's interesting with the prosthetics is you're learning to use the muscles that aren't necessarily there anymore or organized in the same way. Although I guess with the hand they may have the flexors and extensors available for a wrist.
Well, yeah, they do.
Yeah.
That's why we have the electrodes there. But they have no, and the child I'm thinking of is older, so we've developed even less of a homunculus. I mean, it doesn't have it.
Yeah.
If it was traumatic, it would all be, the flexion extension would just be there.
There, yeah. Yeah, I don't think I can offer a specific answer, but it's, I know that Tanisha would be very interested to talk with you. She's originally a prosthetic orthotist and is very interested in the application of some of these. I'm not surprised that it's harder. That makes sense. The broad, arguably maybe more general answer is seeing what kind of feedback works for that individual, because it may be different depending on where the amputation is, what other activities, how they've they've tried to adapt. Have you found that any type of feedback works better? Yeah.
I wish I had the tool I wish I had was a biofeedback. I can have biofeedback. As soon as I put the myoelectric arm on, you know, the contraction happens and I get a quick both ways because it's contracted both sides.
Okay.
So what I'd really like is a biofeedback machine that would give me, you know, a response to the flexor, response to the extensor, and a visual so that you can, you know, when you're still contracting, both things are laid out. I said, okay, well, let's lay it up just the right side, and that's there. It's there. It's just, you know, you don't always have it in your workplace.
Yeah, that's something we can definitely.
Okay.
I can find some people to help with that. Yeah, absolutely.
Maybe we have time for one
more. Okay.
Ben?
Well, I'm just going to say, like, this just confirms so much of what we see our kids do, our children with autism that we work with. I have a boy who has a song for every activity that he does, and so he's got that figured out. By doing self-talk, he does bicycle, bicycle riding, he's bicycling, goes on and on. He almost also has a song for every person that he works with. But with other kids, when we're doing even like bouncing on a therapy ball to help them calm, if we do it with rhythm in our voice, and we can teach EAs to do this as well, like a singing kind of voice, not a harsh voice, and then add counting and numbers to it, just give them more feedback to what they're doing, and it matches with the feedback we're doing from the therapy ball, etc. And you can figure out, like you said, which of those works for each individual child. You just have to figure that out as an observing, and then teach that to the adults that are working with that child so that they get the best out of it. So it's great that there's the evidence that that matches with what we see.
Yeah, I think that's because for me a lot of times if we can't rely solely on the RCTs. I always tell like things get developed. You can't wait for the next 20 to 30 years for us to come up with enough RCTs to say this is how you should teach. And in the end, it's still an individual. And so I always get excited when things converge because I think it means that we're starting to put the pieces of the puzzle together.
All right, thank you so much, Cheryl. That is very high level. And are you around for a few more minutes if people had more questions? So our next presenter, Karen Oswald, will start at 2:30. So we can take a little break. I just want to make a note that this part of the presentation will be posted on the RCC YouTube channel for those of you watching on the webinar. So if you need to get notes or anything like that. The second presentation will not be posted on the YouTube channel because it's a presentation about a conference that Karen went to. So just making that clear. So we're going to take a break from the webinar now until 2:30 so the webinar participants can do what they need to do. And everyone here can take a bathroom break. The bathrooms are down the hall. There's water in the kitchen area. Cheryl will be here for a few more minutes for questions. And thanks again very much. Okay. You must be...